Okay, so this is joint work with Michael Cohen, John Kellner, John Peebles, Richard Peng, and Aaron Sidford. And today I'm going to tell you about how to compute stationary distributions by leveraging directed spectral graph theory. But first, let me just take a brief detour through spectral graph theory and tell you why it's important. So in spectral graph theory, what do? Typically, we work with combinatorial objects, which are graphs. And a graph has an adjacency matrix. Using this adjacency matrix, I can define the following object, the Laplacian of the graph, by subtracting this adjacency matrix from the diagonal matrix whose entries are the weighted degrees of vertices. This is going to be the Laplacian matrix, and this is going to be the fundamental algebraic object that I'm going to associate to this graph. So as computer scientists, in the first case, in the combinatorial world, we care about solving various problems like shortest paths, spanning trees, max flow, min cost flow, and so on. The fundamental problem that's associated to these Laplacian matrices is naturally solving linear systems involving it. And typically, you'd say that, okay, how do you solve such linear systems? We use Gaussian elimination, fast matrix multiplication, and so on. But it turns out that it's actually much easier, as Pilman-Teng has shown in 2004, that we can do this thing in near linear time. And also Rasmus showed you a few minutes ago. And this thing was followed by many subsequent improvements. But what's important about this was that the power of solving these Laplacian systems could be leveraged, because we could use it as a subroutine in order to provide improved running times for many of those problems on the left-hand side. And you can see here that there's a very long list. There is only one issue with this. All of these problems are in nature undirected. Even those that solve directed graphs, as a matter of fact, they keep solving undirected problems, just because you can notice that the Laplacian matrix is a symmetric object, so it doesn't account for the directed structure of the graphs that it cares about. So if we want to be able to extend this theory to handle directed graphs, we should probably try to define some form of directed spectral graph theory. So this is what we do. So let's consider a directed graph, which has an adjacency matrix. Here, I'm just going to draw the transpose of the adjacency matrix. We can compute the weighted out degrees of the vertices of the graph. And by weighted out degree, I just mean the sum of the weights of the outgoing arcs. And what I do is that I consider from the diagonal matrix, whose entries are those weighted out degrees, I subtract the transpose of this adjacency matrix. And this is what I am going to call the directed Laplacian associated to this graph. This object turns out to be very natural. For instance, let's just divide every weight of an arc by the out degree of the vertex that it leaves from. And those, by performing this transformation, what I'm going to obtain will be the transition probabilities in the random walk matrix associated to this graph. In other words, I can just say that the random walk matrix associated to that graph is just A transpose times the out inverse, just a diagonal scaling of the transpose of the adjacency matrix. And as you can see, because of this directed Laplacian is nothing else but a diagonal scaling of identity matrix minus W. So what's the name of the game? We are going to try to solve linear systems involving matrices of this form. Well, the thing is that in order to ever have a hope of doing something like that, we should at least be able to eyeball the kernel of that matrix. If we don't even know the kernel of that matrix, it kind of seems that all hope is lost. But as you can notice, if we know the kernel of this matrix, in order to know the kernel of this matrix, we'd also better know the stationary distribution of W, right? Just because by definition, the stationary distribution of W belongs to the kernel of I minus W, right? And therefore, the stationary distribution, the kernel of this directed Laplacian is just going to be a scaling of the kernel. So therefore, a scaling of the stationary. But computing the stationary distribution is not a problem that's very easy in general. So it kind of seems that it's game over, right? Because I don't even know how to solve Lx equals 0 efficiently. Well, the thing is that we should not abandon hope, because there is a significant class of directed graphs for which we can actually compute this kernel efficiently. And those graphs are going to be Eulerian graphs. So let me show you this example. So I'm just going to consider this vertex that's part of an Eulerian graph. The sum of weights of edges that are leaving it equals the sum of weights of edges that enter it. And this is going to be the corresponding row and column in the directed Laplacian associated to the Laplacian associated to this graph. As you can see, because my graph is Eulerian, the row sum, okay, first of all, notice that the column sum is 0, just by definition. But because the graph is Eulerian, the row sum is also 0, because the sum of the weights of what enters equals the sum of weights of what leaves, so therefore I get 0. This tells me that the all ones vector lies in both the kernel and the co-kernel of that matrix. So I know the kernel, so now I have some hope of solving linear systems. So the first goal will be to solve linear systems on directed Laplacians associated to Eulerian graphs. And then if this succeeds, then we're going to try to extend this technique to solve directed Laplacians associated to non-Eulerian, strongly connected graphs. Okay, so it turns out that what we managed to achieve is we can solve the first problem in time m to 3/4 times 10 plus mn to 2/3, which is, notice that in the sparse regime, this is n to 1.75. This beats anything that we could ever hope to achieve using fast matrix multiplication. And for the second problem, it turns out that we only need to make a polylogarithmic number of calls to the Eulerian solver, and in order to solve arbitrary, strongly connected Laplacians. And as it turns out, this is not the end of the game, because there's a subsequent improvement that's going to be posted in archive, which gives almost linear time, but I'm not going to talk about it right now. Okay, how do we solve Eulerian Laplacian systems? So because our graphs are Eulerian, we can employ undirected structure. And what do I mean by that? I claim that if a graph is Eulerian, then I can consider the symmetrization of its Laplacian, the Laplacian plus Laplacian transpose over 2. This is going to be a symmetric matrix, but furthermore, it's going to be an undirected Laplacian. And undirected Laplacians are very nice because we know how to solve them. So notice what happens with the corresponding row and column over there, right? I just get something that's part of an undirected Laplacian. And notice that this property does not hold in general for graphs that does not hold at all for graphs that are not Eulerian. I mean, consider this example. It's a very simple example. I have the Laplacian associated to this graph, and I have its symmetrization. I mean, first of all, notice that it's not a Laplacian, just because here I have a negative 1.5, which is larger in absolute value than what I have on the diagonal, right? And as a matter of fact, this is not even PSD. So this kind of strongly motivates the use of Eulerian graphs for our purpose. So what we're going to do, we're going to try to solve the system Lx equals b. The way we do that is that we turn the system into the equivalent system L transpose u pseudo inverse Lx equals L transpose u pseudo inverse b. If I find a solution to this, then I'm done. And this system kind of makes sense. It's in some way a sane way of preconditioning the linear system. First of, and this matrix on the left-hand side is what I'm going to call the harmonic symmetrization. And there are very good reasons for doing that. I mean, you can, if you just do some algebra, you're going to see that it's in some sense the harmonic mean between L and L transpose. Okay, this is a sane system. First of all, because that matrix on the left-hand side is symmetric and PSD. And the other reason is that, well, if my Laplacian was undirected in the first place, this is just going to be a standard system, ux equals b. So let's just try to throw our basic tools at solving this linear system. So the classical approach is preconditioning, which is something that Rasmus also told you about, right? The general philosophy behind preconditioning is the following: I want to solve a linear system, but I have access to a solver for a matrix that approximates the matrix in my linear system, in the sense that all eigenvalues approximate each other within a factor of kappa. And by throwing standard methods at it, like Chebyshev iteration or conjugate gradient, we can actually get the solution for the system x equals b by using square root kappa iteration. Square root kappa calls to the solver for the matrix that approximates it. So this is what we're going to try to do over here. And we have the following theorem, which states that u the symmetrization, the indirect Laplacian, is a decent preconditioner for the harmonic symmetrization, in the sense that it lower bounds it in the spectral sense, and also that the trace of u pseudo inverse times the harmonic symmetrization is order n squared, which also immediately implies that the harmonic symmetrization is upper bounded by order n squared times u. So by just using what I mentioned before, we know that by using any of these methods, we just require square root of n squared iterations, therefore order n iterations, each of them involving a solve in u, and we get a solution to our system, right? But this gives us running time order n times m, and it doesn't look like we made much progress. But the thing is that it turns out that this statement is actually much stronger, because it actually gives a much stronger, something much stronger about the eigenvalue structure of that matrix. Namely, we don't have way too many large eigenvalues. And because of this, well, precondition conjugate gradient actually does much better. It actually gives us a solution in n to 2/3 iterations. And this sort of analysis you can also see in a note by Spielman and Wu. So it kind of seems that we have an algorithm that runs in time m times n to 2/3. Well, this is not quite true yet. The reason for that is conjugate gradient actually may require high numerical accuracy. It may require a polynomially large number of bits to represent the numbers that computes. And that polynomial overhead may just undo all the progress that we managed to achieve. So basically, instead of doing that, we're just going to throw some other tools at it, like sparsification and low rank updates, which are standard in combinatorial preconditioning. And we actually managed to obtain an algorithm that has the running time I gave you before. And again, I need to mention that in joint work with Anu Prao, we extended this algorithm, and this is a manuscript that's soon going to be posted on archive. So there's exciting work to be done here. This is not the end of the road. Okay, now I told you how to solve Eulerian Laplacian systems. How do you extend to non-Eulerian? Well, okay, the punchline here is that every strongly connected graph is, as a matter of fact, an Eulerian graph in disguise. What I mean by that is that after I perform a diagonal scaling on it, I can turn it into an Eulerian Laplacian. So let's see an example. So first of all, just consider the rescale Laplacian, where I scale it by the diagonal matrix of out degrees. So what I have here is I minus w. And let me consider the stationary probabilities, right, which I'm going to put on the vertices of this graph. If I scale each of the weights on those arcs by the stationary probability on the vertex that that arc leaves from, then I obtain an Eulerian graph. In other words, this is just a diagonal scaling that makes the all ones vector belong to the kernel of this rescaled directed Laplacian. So the thing is that, well, if I know this diagonal scaling, I have an Eulerian graph. I can use my solver, and I get a solution. But I did not know the stationary to begin with, because I mean, as we said, we don't really know how to do it for non-Eulerian graphs. So what do? This looks like a chicken and egg problem. Well, we're going to relax our problem. But first, we're just going to notice that our Eulerian solver actually gives us something slightly stronger. Not only that we can solve Eulerian Laplacians, but we can solve our systems involving what I'm going to call RCDD matrices. But RCDD matrix, I actually mean just the sum between an Eulerian Laplacian and the non-negative diagonal matrix. This is going to be the sort of system that I claim that we can solve using the Eulerian solver. And the way to do that is just via reduction by adding some extra row and column in order to make our matrix correspond to an Eulerian Laplacian, adding some stuff. We obtain an Eulerian linear system, and by solving it, I can just read off the solution to this system involving an RCDD matrix. So the thing is that, okay, what is our goal? Again, our goal was in the first place to find the diagonal scaling x that makes Lx Eulerian, right? So what we're going to do will be to relax the problem. Instead of doing that directly, we are going to allow ourselves to have some slack, in the sense that not only that I want to have a diagonal scaling x, But I can also allow myself to have a small diagonal matrix E that's going to be non-negative, such that this matrix, L plus E times X, is RCDD. RCDD in the sense of what I said before. It's just a Laplacian plus a non-negative diagonal. And, okay, so what we're going to do is that, okay, we can just start with some matrix E that's just a large multiple of the identity. If I just add the large multiple of the identity to our initial direct Laplacian, it's going to be immediately RCDD without scaling it, just by scaling it by the identity. And we're going to iterate. We're going to produce a new iterate, which is going to be a new pair of those diagonal matrices, such that this pair gives us an RCDD matrix, but we make some progress in the matrix E. And then we keep repeating this process a number of times, and then eventually we reach a pair E and X, such that E is actually very close to 0. And the thing is that, well, when this guy is very close to 0, then this is close to my diagonal scaling, the one that I'm seeking. So therefore, I get the stationary distribution. Okay, so how do I do this thing? So remember that we can start with some E and X, such that L plus E times X is our CDD. And because we have an Eulerian solver, we also have access to a solver for this matrix, which is our CDD. Okay, notice that, okay, what I can do is from that diagonal matrix, I can just perform a rank 1 update on it to actually obtain something that looks sane in this context. I can actually perform a rank 1 update on it and obtain a direct Laplacian, right? This is just going to be a sum of 2 direct Laplacians. Okay, and notice that this matrix is just a rank 1 update away from my initial matrix, for which I have a solver. And in that case, I can just leverage a classical tool, which is the Sherman-Morrison formula, which tells me that whenever I have a solver for a matrix, I also have a solver for a matrix and its transpose. I also have a solver for a rank 1 update of that matrix. And this is what we're going to use here. So via the Sherman-Morrison formula, we know that we have a solver for this new linear system involving the sum of these 2 Laplacians. So therefore, if I have a solver for it, I can compute its kernel. And by computing its kernel, I also get the diagonal scaling x prime that makes this Eulerian. So this is going to be Eulerian. And because it's going to be Eulerian, it's also going to be our CDD, right? Just by definition. But notice that this actually gives me a lot of wiggle room over here. Because if I just add back this non-negative rank 1 matrix that I subtracted from E, then my matrix, then L plus C times x prime with this new scaling x prime becomes strongly RCDD, in the sense that there are going to be many diagonal entries of this matrix that are going to be significantly larger than whatever I have on the corresponding rows or columns, right? So therefore, what I can do is that I can reduce the entries of this diagonal matrix E and produce a smaller matrix E prime. I get to reduce its L1 norm. And it turns out that if we do the analysis right, it turns out that we can reduce this thing by about half, and that's how we make progress. So remember what was going on. We start with some pair E and X that's trivially defined. We apply this iteration that I described before, and we only need a polylogarithmic to do this thing a polylogarithmic number of times until we actually get to reduce the diagonal matrix E very drastically, very fast. And after a polylogarithmic number of iterations, we actually get it to be close to 0, and that's how we find our an approximate diagonal scaling that's going to give us our stationary. So this reduction tells us that, well, whenever we have solvers for Eulerian Laplacians, we actually have solvers for strongly connected Laplacians. Okay, so we have applications for our solver. We can compute all sorts of quantities associated to random walk matrices. We can compute personalized page rank vectors, hitting times, commute times, escape probabilities. Notice that all of these quantities involve a solve involving an RCDD matrix, right? And we can also sketch all pairs commute times, just because we have this nice formula which involves a quadratic form in the harmonic symmetrization. And this we can sketch using known techniques, the ones that we use for sketching effective resistances. Okay, so in conclusion, we made the first dent into directed spectral graph theory. So finally, we actually managed to do something that has algorithmic applications. And of course, there are going to be many running time improvements and simplifications, and we're really eager to understand what we can do over there. But what's most important is whether we can find more algorithmic applications to these solvers that would have the same sort of success that undirected Laplacians had. Yep. Oh, yeah, so, okay, so basically the improvement yields an almost linear time for Eulerian solvers. By almost linear time, I mean that the running time is actually O tilde of m times 2 to the square root log kappa, where kappa is the condition number of the Laplacian. So when that condition number is polynomial, this is smaller than m to 1.000001. Oh, okay. And so the way they work is that we introduce directed spectral sparsification. So the Spielman-Tech papers and many things that followed actually use some form of spectral sparsification. Here we define some form of sparsification that works for directed graphs. And then we use some form of squaring solver. So anyway, some of the co-authors are here. So anyway, we can discuss more about this offline. Okay. Yeah, but by an exact solver, I mean, okay, I actually want to get linear convergence. So in order to solve to epsilon accuracy, I want to have some dependence in log 1 over epsilon. But I'm just hiding all those log factors. But this is the general regime that we're solving these things in.